So if I run python harry.py, what we'll see is this sentence in propositional logic, rain and Hagrid. This is the logical representation of what we have here in our Python program of saying and whose arguments are rain and Hagrid. So we're saying rain and Hagrid by encoding that idea. And this is quite common in Python object-oriented programming, where you have a number of different classes, and you pass arguments into them in order to create a new and object, for example, in order to represent this idea. But now what I'd like to do is somehow encode the knowledge that I have about the world in order to solve that problem from the beginning of class, where we talked about trying to figure out who Harry visited and trying to figure out if it's raining or if it's not raining. And so what knowledge do I have? I'll go ahead and create a new variable called knowledge. And what do I know? Well, I know the very first sentence that we talked about was the idea that if it is not raining, then Harry will visit Hagrid. So all right, how do I encode the idea that it is not raining? Well, I can use not and then the rain symbol. So here's me saying that it is not raining. And now the implication is that if it is not raining, then Harry visited Hagrid. So I'll wrap this inside of an implication to say, if it is not raining, this first argument to the implication, well then Harry visited Hagrid. So I'm saying implication, the premise is that it's not raining, and if it is not raining, then Harry visited Hagrid. And I can print out knowledge.formula to see the logical formula equivalent of that same idea. So I run python of harry.py, and this is the logical formula that we see as the result, which is a text-based version of what we were looking at before. That if it is not raining, then that implies that Harry visited Hagrid. But there was additional information that we had access to as well. In this case, we had access to the fact that Harry visited either Hagrid or Dumbledore. So how do I encode that? Well, this means that in my knowledge, I've really got multiple pieces of knowledge going on. I know one thing and another thing and another thing. So I'll go ahead and wrap all of my knowledge inside of an and. And I'll move things on to new lines just for good measure. But I know multiple things. So I'm saying knowledge is an and of multiple different sentences. I know multiple different sentences to be true. One such sentence that I know to be true is this implication, that if it is not raining, then Harry visited Hagrid. Another such sentence that I know to be true is or Hagrid Dumbledore. In other words, so Hagrid or Dumbledore is true, because I know that Harry visited Hagrid or Dumbledore. But I know more than that, actually. That initial sentence from before said that Harry visited Hagrid or Dumbledore, but not both. So now I want a sentence that will encode the idea that Harry didn't visit both Hagrid and Dumbledore. Well, the notion of Harry visiting Hagrid and Dumbledore would be represented like this, and of Hagrid and Dumbledore. And if that is not true, if I want to say not that, then I'll just wrap this whole thing inside of a not. So now these three lines, line 8 says that if it is not raining, then Harry visited Hagrid. Line 9 says Harry visited Hagrid or Dumbledore. And line 10 says Harry didn't visit both Hagrid and Dumbledore, that it is not true that both the Hagrid symbol and the Dumbledore symbol are true. Only one of them can be true. And finally, the last piece of information that I knew was the fact that Harry visited Dumbledore. So these now are the pieces of knowledge that I know, one sentence and another sentence and another and another. And I can print out what I know just to see it a little bit more visually. And here now is a logical representation of the information that my computer is now internally representing using these various different Python objects. And again, take a look at logic.py if you want to take a look at how exactly it's implementing this, but no need to worry too much about all of the details there. We're here saying that if it is not raining, then Harry visited Hagrid. We're saying that Hagrid or Dumbledore is true. And we're saying it is not the case that Hagrid and Dumbledore is true, that they're not both true. And we also know that Dumbledore is true. So this long logical sentence represents our knowledge base. It is the thing that we know. And now what we'd like to do is we'd like to use model checking to ask a query, to ask a question like, based on this information, do I know whether or not it's raining? And we as humans were able to logic our way through it and figure out that, all right, based on these sentences, we can conclude this and that to figure out that, yes, it must have been raining. But now we'd like for the computer to do that as well. So let's take a look at the model checking algorithm that is going to follow that same pattern that we drew out in pseudocode a moment ago. So I've defined a function here in logic.py that you can take a look at called model check. Model check takes two arguments, the knowledge that I already know and the query. And the idea is, in order to do model checking, I need to enumerate all of the possible models. And for each of the possible models, I need to ask myself, is the knowledge base true and is the query true? So the first thing I need to do is somehow enumerate all of the possible models, meaning for all possible symbols that exist, I need to assign true and false to each one of them and see whether or not it's still true. And so here's the way we're going to do that. We're going to start. So I've defined another helper function internally that we'll get to in just a moment. But this function starts by getting all of the symbols in both the knowledge and the query, by figuring out what symbols am I dealing with. In this case, the symbols I'm dealing with are Rain and Hagrid and Dumbledore, but there might be other symbols depending on the problem. And we'll take a look soon at some examples of situations where ultimately we're going to need some additional symbols in order to represent the problem. And then we're going to run this check all function, which is a helper function that's basically going to recursively call itself, checking every possible configuration of propositional symbols. So we start out by looking at this check all function, and what do we do? So if not symbols means if we've finished assigning all of the symbols, we've assigned every symbol a value. So far we haven't done that, but if we ever do, then we check. In this model, is the knowledge true? That's what this line is saying. If we evaluate the knowledge propositional logic formula using the model's assignment of truth values, is the knowledge true? If the knowledge is true, then we should return true only if the query is true. Because if the knowledge is true, we want the query to be true as well in order for there to be entailment. Otherwise, we don't know that otherwise there won't be an entailment if there's ever a situation where what we know in our knowledge is true, but the query, the thing we're asking, happens to be false. So this line here is checking that same idea, that in all worlds where the knowledge is true, the query must also be true. Otherwise, we can just return true, because if the knowledge isn't true, then we don't care. This is equivalent to when we were enumerating this table from a moment ago. In all situations where the knowledge base wasn't true, all of these 7 rows here, we didn't care whether or not our query was true or not. We only care to check whether the query is true when the knowledge base is actually true, which was just this green highlighted row right there. So that logic is encoded using that statement there. And otherwise, if we haven't assigned symbols yet, which we haven't seen anything yet, then the first thing we do is pop one of the symbols. I make a copy of the symbols first, just to save an existing copy. But I pop one symbol off of the remaining symbols so that I just pick one symbol at random. And I create one copy of the model where that symbol is true. And I create a second copy of the model where that symbol is false. So I now have 2 copies of the model, one where the symbol is true and one where the symbol is false. And I need to make sure that this entailment holds in both of those models. So I recursively check all on the model where the statement is true and check all on the model where the statement is false. So again, you can take a look at that function to try to get a sense for how exactly this logic is working. But in effect, what it's doing is recursively calling this check all function again and again and again. And on every level of the recursion, we're saying, let's pick a new symbol that we haven't yet assigned, assign it to true, and assign it to false, and then check to make sure that the entailment holds in both cases. Because ultimately, I need to check every possible world. I need to take every combination of symbols and try every combination of true and false in order to figure out whether the entailment relation actually holds. So that function we've written for you. But in order to use that function inside of harry.py, what I'll write is something like this. I would like to model check based on the knowledge. And then I provide as a second argument what the query is, what the thing I want to ask is. And what I want to ask in this case is it raining? So model check, again, takes 2 arguments. The first argument is the information that I know, this knowledge, which in this case is this information that was given to me at the beginning. And the second argument, rain, is encoding the idea of the query. What am I asking? I would like to ask, based on this knowledge, do I know for sure that it is raining? And I can try and print out the result of that. And when I run this program, I see that the answer is true, that based on this information, I can conclusively say that it is raining, because using this model checking algorithm, we were able to check that in every world where this knowledge is true, it is raining. In other words, there is no world where this knowledge is true and it is not raining. So you can conclude that it is, in fact, raining. And this sort of logic can be applied to a number of different types of problems. That if confronted with a problem where some sort of logical deduction can be used in order to try to solve it, you might try thinking about what propositional symbols you might need in order to represent that information, and what statements in propositional logic you might use in order to encode that information which you know. And this process of trying to take a problem and figure out what propositional symbols to use in order to encode that idea, or how to represent it logically, is known as knowledge engineering. That software engineers and AI engineers will take a problem and try and figure out how to distill it down into knowledge that is representable by a computer. And if we can take any general purpose problem, some problem that we find in the human world, and turn it into a problem that computers know how to solve, as by using any number of different variables, well then we can take a computer that is able to do something like model checking or some other inference algorithm and actually figure out how to solve that problem. So now we'll take a look at 2 or 3 examples of knowledge engineering in practice, of taking some problem and figuring out how we can apply logical symbols and use logical formulas to be able to encode that idea. And we'll start with a very popular board game in the US and the UK known as Clue. Now, in the game of Clue, there's a number of different factors that are going on. But the basic premise of the game, if you've never played it before, is that there are a number of different people. For now, we'll just use 3, Colonel Mustard, Professor Plum, and Miss Scarlet. There are a number of different rooms, like a ballroom, a kitchen, and a library. And there are a number of different weapons, a knife, a revolver, and a wrench. And 3 of these, 1 person, 1 room, and 1 weapon, is the solution to the mystery, the murderer and what room they were in and what weapon they happened to use. And what happens at the beginning of the game is that all these cards are randomly shuffled together, and 3 of them, 1 person, 1 room, and 1 weapon, are placed into a sealed envelope that we don't know. And we would like to figure out, using some sort of logical process, what's inside the envelope, which person, which room, and which weapon. And we do so by looking at some, but not all, of these cards here, by looking at these cards to try and figure out what might be going on. And so this is a very popular game, but let's now try and formalize it and see if we could train a computer to be able to play this game by reasoning through it logically. So in order to do this, we'll begin by thinking about what propositional symbols we're ultimately going to need. Remember again that propositional symbols are just some symbol, some variable, that can be either true or false in the world. And so in this case, the propositional symbols are really just going to correspond to each of the possible things that could be inside the envelope. Mustard is a propositional symbol that in this case will just be true if Colonel Mustard is inside the envelope, if he is the murderer, and false otherwise. And likewise for Plum for Professor Plum, and Scarlet for Miss Scarlet, and likewise for each of the rooms and for each of the weapons. We have 1 propositional symbol for each of these ideas. Then using those propositional symbols, we can begin to create logical sentences, create knowledge that we know about the world. So for example, we know that someone is the murderer, that one of the 3 people is in fact the murderer. And how would we encode that? Well, we don't know for sure who the murderer is, but we know it is 1 person, or the 2nd person, or the 3rd person. So I could say something like this: Mustard, or Plum, or Scarlet. And this piece of knowledge encodes that one of these 3 people is the murderer. We don't know which, but one of these 3 things must be true. What other information do we know? Well, we know that, for example, one of the rooms must have been the room in the envelope, that the crime was committed either in the ballroom or the kitchen or the library. Again, right now, we don't know which, but this is knowledge we know at the outset, knowledge that one of these 3 must be inside the envelope. And likewise, we can say the same thing about the weapon, that it was either the knife or the revolver or the wrench, that one of those weapons must have been the weapon of choice and therefore the weapon in the envelope. And then as the game progresses, the gameplay works by people get various different cards, and using those cards, you can deduce information. That if someone gives you a card, for example, I have the Professor Plum card in my hand, then I know the Professor Plum card can't be inside the envelope. I know that Professor Plum is not the criminal, so I know a piece of information like not Plum, for example. I know that Professor Plum has to be false. This propositional symbol is not true. And sometimes I might not know for sure that a particular card is not in the middle, but sometimes someone will make a guess and I'll know that one of 3 possibilities is not true. Like someone will guess Colonel Mustard in the library with the revolver or something to that effect. And in that case, a card might be revealed that I don't see, but if it is a card and it is either Colonel Mustard or the revolver or the library, then I know that at least one of them can't be in the middle. So I know something like it is either not Mustard, or it is not the library, or it is not the revolver. Now, maybe multiple of these are not true, but I know that at least one of mustard, library, and revolver must, in fact, be false. And so this now is a propositional logic representation of this game of Clue, a way of encoding the knowledge that we know inside this game using propositional logic that a computer algorithm, something like model checking that we saw a moment ago, can actually look at and understand. So let's now take a look at some code to see how this algorithm might actually work in practice. All right, so I'm now going to open up a file called clue.py, which I've started already. And what we'll see here is I've defined a couple of things. I've defined some symbols initially. Notice I have a symbol for Colonel Mustard, a symbol for Professor Plum, a symbol for Miss Scarlet, all of which I've put inside of this list of characters. I have a symbol for ballroom and kitchen and library inside of a list of rooms. And then I have symbols for knife and revolver and wrench. These are my weapons. And so all of these characters and rooms and weapons all together, those are my symbols. And now I also have this check knowledge function. And what the check knowledge function does is it takes my knowledge and it's going to try and draw conclusions about what I know. So for example, we'll loop over all of the possible symbols and we'll check, do I know that that symbol is true? And a symbol is going to be something like Professor Plum or the knife or the library. And if I know that it is true, in other words, I know that it must be the card in the envelope, then I'm going to print out using a function called cprint, which prints things in color. I'm going to print out the word yes, and I'm going to print that in green, just to make it very clear to us. And if we're not sure that the symbol is true, maybe I can check to see if I'm sure that the symbol is not true. Like if I know for sure that it is not Professor Plum, for example. And I do that by running model check again, this time checking if my knowledge is not the symbol, if I know for sure that the symbol is not true. And if I don't know for sure that the symbol is not true, because I say elif not model check, meaning I'm not sure that the symbol is false, well, then I'll go ahead and print out maybe next to the symbol. Because maybe the symbol is true, maybe it's not, I don't actually know. So what knowledge do I actually have? Well, let's try and represent my knowledge now. So my knowledge is, I know a couple of things, so I'll put them in an and. And I know that one of the 3 people must be the criminal. So I know or Mustard, Plum, Scarlet. This is my way of encoding that it is either Colonel Mustard or Professor Plum or Miss Scarlet. I know that it must have happened in one of the rooms. So I know or ballroom, kitchen, library, for example. And I know that one of the weapons must have been used as well. So I know or knife, revolver, wrench. So that might be my initial knowledge, that I know that it must have been one of the people, I know it must have been in one of the rooms, and I know that it must have been one of the weapons. And I can see what that knowledge looks like as a formula by printing out knowledge.formula. So I'll run python clue.py. And here now is the information that I know in logical format. I know that it is Colonel Mustard or Professor Plum or Miss Scarlet. And I know that it is the ballroom, the kitchen, or the library. And I know that it is the knife, the revolver, or the wrench. But I don't know much more than that. I can't really draw any firm conclusions. And in fact, we can see that if I try and do, let me go ahead and run my knowledge check function on my knowledge. Knowledge check is this function that or check knowledge rather, is this function that I just wrote that looks over all of the symbols and tries to see what conclusions I can actually draw about any of the symbols. So I'll go ahead and run clue.py and see what it is that I know. And it seems that I don't really know anything for sure. I have all 3 people are maybes, all 3 of the rooms are maybes, all 3 of the weapons are maybes. I don't really know anything for certain just yet. But now let me try and add some additional information and see if additional information, additional knowledge, can help us to logically reason our way through this process. And we are just going to provide the information. Our AI is going to take care of doing the inference and figuring out what conclusions it's able to draw. So I start with some cards, and those cards tell me something. So if I have the Colonel Mustard card, for example, I know that the mustard symbol must be false. In other words, mustard is not the one in the envelope, is not the criminal. So I can say knowledge supports something called, every and in this library supports .add, which is a way of adding knowledge or adding an additional logical sentence to an and clause. So I can say knowledge.add, not mustard. Right? I happen to know, because I have the mustard card, that Colonel Mustard is not the suspect. And maybe I have a couple of other cards too. Maybe I also have a card for the kitchen, so I know it's not the kitchen. And maybe I have another card that says that it is not the revolver. So I have 3 cards, Colonel Mustard, the kitchen, and the revolver, and I encode that into my AI this way by saying it's not Colonel Mustard, it's not the kitchen, and it's not the revolver, and I know those to be true. So now, when I rerun clue.py, we'll see that I've been able to eliminate some possibilities. Before, I wasn't sure if it was the knife or the revolver or the wrench. The knife was maybe, revolver was maybe, wrench is maybe. Now I'm down to just the knife and the wrench. Between those two, I don't know which one it is. They're both maybes. But I've been able to eliminate the revolver, which is one that I know to be false because I have the revolver card. And so additional information might be acquired over the course of this game, and we would represent that just by adding knowledge to our knowledge set, our knowledge base that we've been building here. So if, for example, we additionally got the information that someone made a guess. Someone guessed, like, Miss Scarlet in the library with the wrench. And we know that a card was revealed, which means that one of those 3 cards, either Miss Scarlet or the library or the wrench, one of those at minimum must not be inside of the envelope. So I could add some knowledge. Say knowledge.add. And I'm going to add an or clause, because I don't know for sure which one it's not, but I know one of them is not in the envelope. So it's either not Scarlet, or it's not the library, and or supports multiple arguments. I can say it's also or not the wrench. So at least one of those needs Scarlet, library, and wrench. At least one of those needs to be false. I don't know which, though. Maybe it's multiple, maybe it's just one, but at least one I know needs to hold. And so now if I rerun clue.py, I don't actually have any additional information just yet. Nothing I can say conclusively. I still know that maybe it's Professor Plum, maybe it's Miss Scarlet. I haven't eliminated any options. But let's imagine that I get some more information, that someone shows me the Professor Plum card, for example. So I say, all right, let's go back here, knowledge.add, not Plum. So I have the Professor Plum card. I know that Professor Plum is not in the middle. I rerun clue.py, and all right, now I'm able to draw some conclusions. Now I've been able to eliminate Professor Plum, and the only person it could remaining be is Miss Scarlet. So I know, yes, Miss Scarlet, this variable must be true. And I've been able to infer that based on the information I already had. Now between the ballroom and the library and the knife and the wrench, for those two, I'm still not sure. So let's add one more piece of information. Let's say that I know that it's not the ballroom. Someone has shown me the ballroom card, so I know it's not the ballroom, which means at this point I should be able to conclude that it's the library. Let's see. I'll say knowledge.add, not the ballroom. And we'll go ahead and run that. And it turns out that after all of this, not only can I conclude that I know that it's the library, but I also know that the weapon was the knife. And that might have been an inference that was a little bit trickier, something I wouldn't have realized immediately. But the AI, via this model checking algorithm, is able to draw that conclusion, that we know for sure that it must be Miss Scarlet in the library with the knife. And how did we know that? Well, we know it from this or clause up here, that we know that it's either not Scarlet, or it's not the library, or it's not the wrench. And given that we know that it is Miss Scarlet, and we know that it is the library, then the only remaining option for the weapon is that it is not the wrench, which means that it must be the knife. So we as humans now can go back and reason through that, even though it might not have been immediately clear. And that's one of the advantages of using an AI or some sort of algorithm in order to do this, is that the computer can exhaust all of these possibilities and try and figure out what the solution actually should be. And so for that reason, it's often helpful to be able to represent knowledge in this way. Knowledge engineering, some situation where we can use a computer to be able to represent knowledge and draw conclusions based on that knowledge. And anytime we can translate something into propositional logic symbols like this type of approach can be useful. So you might be familiar with logic puzzles, where you have to puzzle your way through trying to figure something out. This is what a classic logic puzzle might look like. Something like Gilderoy, Minerva, Pomona, and Horace each belong to a different one of the 4 houses: Gryffindor, Hufflepuff, Ravenclaw, and Slytherin. And then we have some information that Gilderoy belongs to Gryffindor or Ravenclaw, Pomona does not belong in Slytherin, and Minerva does belong to Gryffindor. So we have a couple pieces of information, and using that information, we need to be able to draw some conclusions about which person should be assigned to which house. And again, we can use the exact same idea to try and implement this notion. So we need some propositional symbols. And in this case, the propositional symbols are going to get a little more complex, although we'll see ways to make this a little bit cleaner later on. But we'll need 16 propositional symbols, one for each person and house. So we need to say, remember, every propositional symbol is either true or false. So Gilderoy Gryffindor is either true or false. Either he's in Gryffindor or he is not. Likewise, Gilderoy Hufflepuff, also true or false. Either it is true or it's false. And that's true for every combination of person and house that we could come up with. We have some sort of propositional symbol for each one of those. Using this type of knowledge, we can then begin to think about what types of logical sentences we can say about the puzzle. That if we know, before we even think about the information we were given, we can think about the premise of the problem, that every person is assigned to a different house. So what does that tell us? Well, it tells us sentences like this. It tells us like, Pomona Slytherin implies not Pomona Hufflepuff. Something like, if Pomona is in Slytherin, then we know that Pomona is not in Hufflepuff. And we know this for all 4 people and for all combinations of houses, that no matter what person you pick, if they're in one house, then they're not in some other house. So I'll probably have a whole bunch of knowledge statements that are of this form, that if we know Pomona is in Slytherin, then we know Pomona is not in Hufflepuff. We were also given the information that each person is in a different house. So I also have pieces of knowledge that look something like this. Minerva Ravenclaw implies not Gilderoy Ravenclaw. If they're all in different houses, then if Minerva is in Ravenclaw, then we know that Gilderoy is not in Ravenclaw as well. And I have a whole bunch of similar sentences like this that are expressing that idea for other people and other houses as well. And so in addition to sentences of these form, I also have the knowledge that was given to me. Information like Gilderoy was in Gryffindor or in Ravenclaw that would be represented like this, Gilderoy Gryffindor or Gilderoy Ravenclaw. And then using these sorts of sentences, I can begin to draw some conclusions about the world. So let's see an example of this. We'll go ahead and actually try and implement this logic puzzle to see if we can figure out what the answer is. I'll go ahead and open up puzzle.py, where I've already started to implement this sort of idea. I've defined a list of people and a list of houses, and I've so far created one symbol for every person and for every house. That's what this double for loop is doing, looping over all people, looping over all houses, creating a new symbol for each of them. And then I've added some information. I know that every person belongs to a house, so I've added the information for every person, that person Gryffindor or person Hufflepuff or person Ravenclaw, or person Slytherin, that one of those 4 things must be true. Every person belongs to a house. What other information do I know? I also know that only one house per person. So no person belongs to multiple houses. So how does this work? Well, this is going to be true for all people. So I'll loop over every person. And then I need to loop over all different pairs of houses. The idea is I want to encode the idea that if Minerva is in Gryffindor, then Minerva can't be in Ravenclaw. So I'll loop over all houses, h1, and I'll loop over all houses again, h2. And as long as they're different, h1 not equal to h2, then I'll add to my knowledge base this piece of information. That implication, in other words, an if-then, if the person is in h1, then I know that they are not in house h2. So these lines here are encoding the notion that for every person, if they belong to house 1, then they are not in house 2. And the other piece of logic we need to encode is the idea that every house can only have one person. In other words, if Pomona is in Hufflepuff, then nobody else is allowed to be in Hufflepuff either. And that's the same logic, but sort of backwards. I loop over all of the houses and loop over all different pairs of people. So I loop over people once, loop over people again, and only do this when the people are different, p1 not equal to p2. And I add the knowledge that if, as given by the implication, if person 1 belongs to the house, then it is not the case that person 2 belongs to the same house. So here I'm just encoding the knowledge that represents the problem's constraints. I know that everyone's in a different house. I know that any person can only belong to one house. And I can now take my knowledge and try and print out the information that I happen to know. So I'll go ahead and print out knowledge.formula just to see this in action. And I'll go ahead and skip this for now, but we'll come back to this in a second. Let's print out the knowledge that I know by running Python puzzle.py. It's a lot of information, a lot that I have to scroll through, because there's 16 different variables all going on. But the basic idea, if we scroll up to the very top, is I see my initial information. Gilderoy is either in Gryffindor, or Gilderoy is in Hufflepuff, or Gilderoy is in Ravenclaw, or Gilderoy is in Slytherin, and then way more information as well. So this is quite messy, more than we really want to be looking at. And soon, too, we'll see ways of representing this a little bit more nicely using logic. But for now, we can just say these are the variables that we're dealing with. And now we'd like to add some information. So the information we're going to add is Gilderoy is in Gryffindor, or he is in Ravenclaw. So that knowledge was given to us. So I'll go ahead and say knowledge.add. And I know that either or Gilderoy Gryffindor or Gilderoy Ravenclaw. One of those two things must be true. I also know that Pomona was not in Slytherin, so I can say knowledge.add not this symbol, not the Pomona Slytherin symbol. And then I can add the knowledge that Minerva is in Gryffindor by adding the symbol Minerva Gryffindor. So those are the pieces of knowledge that I know. And this loop here at the bottom just loops over all of my symbols, checks to see if the knowledge entails that symbol by calling this model check function again. And if it does, if we know the symbol is true, we print out the symbol. So now I can run Python puzzle.py, and Python is going to solve this puzzle for me. We're able to conclude that Gilderoy belongs to Ravenclaw, Pomona belongs to Hufflepuff, Minerva to Gryffindor, and Horace to Slytherin, just by encoding this knowledge inside the computer, although it was quite tedious to do in this case. And as a result, we were able to get the conclusion from that as well.